Antaray. Everything flows, everything moves. This is the message of Heraclitus, 2,500 years ago. The air around us contains a large number of molecules that constantly collide, like billiard balls. Everything moves. Even my rocking chair is carried by the Earth in its race around the Sun. For years, humans have observed these movements and gradually have tried to predict them. First astrologers, then scientists, and especially mathematicians. By the way, many mathematicians have cast horoscopes. Using the motion of the stars to predict our future is an old dream. In the mathematical world about us as well, everything is in motion. Look at the cue ball. Stop. Can you guess where it will be in 2 seconds? Of course, it continues straight on, like so. That prediction was easy. This time, things are a bit harder. Stop. Obviously, the ball will hit the edge of the billiard table. Where will it go next? Mathematicians can calculate the future position of the ball as a function of time. This is already a success for science. They can even calculate what happens when two balls collide. Gradually, the idea of determinism has imposed itself on science. If I know the situation now, then, in principle, I should be able to determine the situation a bit later. Here, for example, what will be the path of the cue ball? In the game of billiards, the player must hit the two balls with the cue ball. Not bad. And what will happen here? Not bad either. If I read the paper today, can I predict in principle what will happen in the world a month from now? Of course not. You must not think that this film will help you predict the future. Let's go back to the billiard table, but now with 50 balls on it. Imagine a perfect table where the balls roll without friction. After the cue strikes the cue ball, the movement is complicated. Can we predict this movement? Of course we can. After all, our computer made these images. But it made many, many calculations. It's clear that the balls follow rectilinear trajectories as they bounce off of each other. There are many collisions, but if we take enough time, or we calculate very quickly, we can predict their trajectories step by step, collision after collision. The computer can easily calculate the position of the cue ball in 1 hour, for example. But this takes so many calculations that it far exceeds the abilities of a human being. Prediction in principle, perhaps. But in practice? Let's move one of the balls a few centimeters. The two pool tables are almost identical. Only one ball is slightly out of place. When we hit the cue ball, the movement on both tables starts off the same way. But after a little while, not too long, the trajectories become completely different. If we want to predict the future of the cue ball, we can do so. But we need to know in detail the positions of all the balls on the table, and there are so many of them. A small uncertainty about a single ball shatters any hope of determining the future path of the cue ball. Here is the classic definition of determinism by the mathematician Laplace in 1814.
We must consider the present state of the universe as the effect of its previous state, and as the cause of what will follow. An intelligence which at a given moment would know all the forces by which nature is animated, and the position of every object in the universe, if indeed it was powerful enough to submit this data to analysis, would embrace in a single formula the movements of the greatest bodies of the universe and those of the lightest atom. Nothing would be uncertain for it, and the future as the past would appear before its eyes.
How can we understand the movements of celestial bodies? Watch this computer simulation of a fictional solar system with 2 suns and just 1 planet. It's a bit like our billiard table. The computer can calculate, step by step, the movement, but can it predict the fate of the system? Will the small planet one day collide with one of the suns? So, we could predict the future if we had infinite intelligence. This is not the case, unfortunately. Or perhaps, fortunately. So, what can science do if it cannot predict the future? Well, if we are willing to be less ambitious and more modest, we can still make some very useful forecasts. This requires a different view on determinism. We will not try to predict the future position of a ball amongst a cloud of other balls, but rather look for a probability. The purpose of the forecast is no longer to determine the temperature in Paris on a specific day 10 years in the future, for that is impossible, but rather to try and predict averages, statistics. For example, the number of hurricanes crossing the Atlantic in one season. Probabilities rather than certainties? That is a big change in perspective. There is a whole world between theory and practice. It is October 26, 1676, and Isaac Newton is writing a letter to his great rival Leibniz. He wants to talk about his greatest discovery, but at the same time, he wants to keep it a secret. So instead, he sends a riddle. 6a, 2c, d, ae, 13e, 2f, 7i, 3l, 9n, 4o, 4q, 2r, 4s, 8t, 12v, x. Leibniz did not decode this message, but science historians have now decrypted the Latin phrase that was hiding in the anagram.
Data equatione quodcunque, fluentes quantitates involvente, fluxiones invenire et vice versa.
In English, given an equation in any number of variables, find its derivative and vice versa. This is the differential and integral calculus, a crystal ball that is incredibly effective for predicting the future. It lets you calculate the future movement of a system when you know its present state and the forces that act on it. It is about solving a differential equation and finding solutions. Let's look at this in a world made of Lego. After all, the mathematical world is a bit like a game, where everything is simpler than in real life, a world that is sometimes even a bit childlike. The footprints indicate the paths followed by the athletes, their trajectories. Suppose that our Lego athletes take steps at a steady pace, but some have steps that are long, while some have steps that are short. For the athletes that go quickly, 2 consecutive footprints are far apart. For the ones that go slowly, the steps are close together. The arrow joining 2 consecutive steps indicates the speed. It is the difference between 2 positions at 2 consecutive moments, hence the phrase differential calculus. A 100-meter race. Who will win? "9.58 seconds. Bravo!" Now, movement rarely consists of discrete steps. Consider these moving race cars. They roll, they don't take steps. What then do we mean by speed? One idea is to recall that this film consists of 25 frames per second. So we can think of the motorbike as taking 25 steps every second. Hence, we can talk about its speed, just like we were talking about the speed of the Lego runners. Newton approximates any continuous motion as a sequence of stepwise movements, but with steps that become so small that they become invisible, just like in the movies. Calculating the speed of a motion is called calculating a derivative. It is the goal of differential calculus. Here then are some movements. These arrows indicate the speed, and mathematicians call them vectors. Now imagine the opposite problem. Look at the arrows drawn on the floor. Mathematicians call this a vector field. Imagine a field of wheat, but instead of stalks of wheat, we have vectors. The Lego people's mission is to move with speed as indicated by the vector field. Easy, you say. They look under their feet and they see a vector, which tells them how to move. Then they set off in that direction and at that speed. A brief moment later, they've arrived at a new point with a new direction and speed, and off they go again. They do this over and over again. Walking is not difficult. Just put one foot in front of the other and do it again. Actually, we should explain what we mean by a brief moment later. Newton's answer would be an infinitely brief moment. We already saw that a continuous movement is not the same thing as a succession of steps. It's what you get when the steps become smaller and smaller. So, rather than hopping like a Lego person, take a car that rides continuously. You will follow what is called a trajectory, a curve that is tangent to the vector field everywhere. Here you have a vector field in the plane and 2 points that are the initial positions of the 2 motorcycles. The theorem of Cauchy-Lipschitz summarizes the concept of determinism. It claims that the starting points determine the future trajectories. From each point, there is a unique trajectory whose initial position is the given point. Each point has its destiny, different for everyone. The Lego man faces his fate. All he can do is follow his trajectory. Note that two trajectories can never cross. Determining the trajectory from the knowledge of the velocity field is the work of integral calculus. Thus it goes in the opposite direction from differential calculus. Here's a group of Lego people neatly ordered, our little soldiers ready to start walking. Off they go. You see that the nice original order gets destroyed. It is sometimes said that one determines the flow of a field as if these characters were floating on a river, each following their course in the current. Think of the flow of humanity, those 7 billion Lego people moving all over the Earth, or think of the flow of billions of billions of billions of molecules in the Earth's atmosphere. Here is a simple example, almost naive, which will show us a weakness of determinism. Watch this vector field. The figures move forward and, as you can see, those on the left of the central line turn to the left, and those on the right of the central line turn to the right. In a way, determinism is valid. Everyone follows his destiny over which he has no control. But on the other hand, two men starting very close to each other can have very different destinies. A little thing can completely change the future. In his little book, Matter and Motion, published in 1876, the physicist Maxwell stresses the sensitivity of physical phenomena to initial conditions. Here is what he writes. There is a maxim that the same causes will always produce the same effects. There is another maxim, which must not be confounded with the first, which asserts that like causes produce like effects. This is only true when small variations in the initial circumstances produce only small variations in the final state of the system. In a great many physical phenomena, this condition is satisfied, but there are other cases in which a small initial variation may produce a very great change in the final state of the system. For instance, a small difference in the speed of the car may cause an accident. This dependence of the future on initial conditions is only one aspect of chaos. But there are much more complex situations. Imagine, for example, a vector field which is no longer drawn on the ground, but is drawn in space. This one, for example, shown on a vertical plane moving back and forth. Now our Legos don't walk. Instead, they fly in their spaceships. At every moment, their speed is determined by the vector field. See what happens to our poor Lego astronauts. This is much more chaotic. Can we imagine a fortune teller who can divine the future position of the spaceship? It is impossible on such a roller coaster. Its predictions would be mere deceptions. Where will the ship be in an hour? No one can tell. If it is difficult to predict the future of a Lego astronaut, just imagine predicting the future of a human being. At the age of 17, Newton wondered why an apple falls from an apple tree, while the moon does not fall to the earth. Until that time, people thought that objects on Earth, such as apples, did not follow the same laws as celestial bodies. Comparing the motion of the moon and an apple, and thinking that there might be universal physical laws valid on Earth as well as in the skies, was a revolution. Before Newton, physics was dominated by the thoughts of Aristotle. Aristotle suggested that each object had its proper place. If we move it from that place, it will do its best to return to it. Everything around us seeks its natural balance. An apple tends to go down, since that is its nature. The moon orbits the Earth because that is its nature. In fact, understanding falling objects is not so easy. By the way, folks in cartoons also have problems with physics. Here is the first law of physics in cartoons. Any object suspended in space remains motionless until it becomes aware of the situation. And according to a cartoonist at Disney, cartoons follow the laws of physics, unless the opposite is funnier. Newton came up with a universal law of gravitation. Two bodies attract with a force proportional to each of their masses and inversely proportional to the square of the distance between them. Where does this force of attraction come from? How can it be explained? How can two objects, separated by billions of kilometers, attract each other seemingly instantaneously? This mystery was not explained until much later, and only in part, by Albert Einstein. All objects, an apple as well as the moon, are attracted by the Earth. The force of gravity affects everything that surrounds us. Another great idea from Newton is that forces modify speeds. When a speed increases, we say that the object accelerates. So, Imagine an apple affected by one force only, its weight. In the vicinity of the apple tree, gravity is essentially constant. At the moment that the twig breaks, the apple has speed equal to 0. But the force of gravity changes the speed. The apple falls faster and faster and crashes to the ground. Newton goes further. He explains how, if we know the forces, we can calculate a trajectory. Here is a ball rolling on a plane. What will happen to it? Nothing. It will continue to roll at a constant speed. This statement, found in physics books, is true, naturally, except in that it does not match what we observe in day-to-day life. A billiard ball will eventually stop because frictional forces slow it down. But let's ignore those forces. When the ball is in contact with the ground reacts and applies a force in the opposite direction, preventing the ball from piercing the ground. So the total force acting on the ball is 0. If there is no force, there is no change in speed, and so the speed remains constant, as we have seen before. However, when the ground gives way, the ball is still subject to the force of gravity, that is, its weight, which now changes the speed. This is because there is no ground left to counteract the weight. Newton expressed all of this in one of the most important formulas of physics. F equals ma. F is the force, m is the mass of the object, and a is the acceleration. The acceleration is the rate at which the speed changes. In other words, the derivative of the speed. In our situation, the force of gravity is constant, directed downwards. So the acceleration is constant and directed downwards. The velocity vector will increase every second by the addition of a constant vector. Look at the trajectory. It's a parabola. If we know the forces that are applied to a system, we know the acceleration. If we also know the initial position and the initial speed, we can then predict the future movement. If you aim very well, and if you choose the right initial conditions, you can get incredible motions. An initial condition is not just an initial position, but also an initial speed. Look here. We have 3 planets without a sun following 3 closed trajectories. The motion is periodic. Here things are more interesting. The 3 planets share the same trajectory. And here, the 3 planets also follow the same trajectory, a figure of 8. This is a planetary dance. It must be said that such an elegant ballet is difficult to choreograph. In order to arrange it, we have to aim very well, as in billiards. If we change the initial conditions just a little bit, wham! The beautiful choreography turns into chaos. By the way, if the moon is really attracted to the Earth, the way an apple is, why doesn't it fall to the Earth the way an apple does? Newton's answer is amazing. It does fall. If we observe what happens in the vicinity of the Earth, the force of gravity is not constant. It is always directed towards the center of the Earth and is less and less strong as we move away from the Earth. The Earth attracts the Moon by a gravitational force which influences its trajectory. However, because this is combined with a rotation, the Moon is constantly falling and never reaching its goal. If the Moon were not subject to any force, it would move in a straight line, ignoring the Earth completely. So let's take a fictitious Moon at 384,000 kilometers above the Earth and let it loose. It falls. Second attempt. Let's launch the same Moon with a small initial horizontal speed. The trajectory deviates slightly, but we have not avoided the catastrophe. With a higher initial speed, the Moon misses the Earth narrowly and continues turning around it periodically. A higher speed yet, and the Moon rotates on a circular orbit, more or less what happens in reality. Too high a speed and goodbye Moon. The solar system has 8 main planets and thousands of secondary objects, all interacting with one another via gravity. In the study of such a system, the description of the initial conditions will involve many positions and many speeds. And just imagine all the data necessary to describe the motion of the atmosphere with its countless molecules. Studying the trajectories of a vector field that depend on a large number of variables, this is the real challenge launched by the great Newton. Simple things first. In the 16th century, Galileo observed a swaying lamp and measured its oscillation period by taking his own pulse. How can we describe a swinging pendulum? The tip of the pendulum moves on the blue circle. Let's place this circle on the cylinder, like so. Every point of the circle represents a position of the pendulum. The red point, for example, is the position at the bottom. Its speed, given by the red vector, is described by a number. The number is positive if it rotates in one direction, and negative if it rotates in the other. We can represent this number in the cylinder's vertical position. So, a single point on the cylinder describes both the position and the speed. The first coordinate, on the circle, tells us where the swing is, and the second, vertical coordinate, tells us how fast it is swinging. So now, let's put gravity to work and watch the swing. For now, we will assume there is no friction at all. The swinging will never end. If the initial position is low, and the initial velocity is not too large, then the pendulum moves periodically. We all know that. If we launch it faster, perhaps too fast, it will go all the way around. It is still a periodic movement, but not in the same way. Look at the trajectory on the cylinder. It follows a vector field. Now observe the more realistic situation, where there is friction. The oscillation slowly decreases, and then finally the pendulum slows to a stop. Remember Aristotle's theory. The swing is now back in its natural position at the bottom. Observe the corresponding vector field on the cylinder. Trajectories eventually spiral into the resting position. This equilibrium position is called a stable attractor. A swing with friction is not very much fun because it eventually stops. So we have to give the swing a push to make it go really high. This is also the point of view of the gentleman represented by the painter Fragonard. He seems very interested in the swing. Let's imagine that the pendulum, in addition to gravity and friction, is also subjected to a pushing force coming from a small nozzle. This is a very modern pendulum. It comes with a jet engine. For example, suppose the nozzle activates only when the speed and the height of the pendulum are lower than a certain value. If we start too slowly, we are pushed, and we accelerate and accelerate until the pushing stops because the pendulum is going too fast. Friction takes over, and it slows down until the push comes to the rescue again, and so on. The motion finally stabilizes on a periodic regime. Poincaré calls this a limit cycle. This is the opposite of chaos, in a way, the periodic regime. Everything is in sync. Here is what is called the phase portrait of the cylinder. The limit cycle is in red. We see a spiraling trajectory that gradually becomes the periodic trajectory. Here is a simple example that illustrates all of this in ecology. The Lotka-Volterra model, dating from the 1930s. Two populations share a territory. For example, rabbits and foxes. We will instead imagine a pond with ducks and water lilies. See the ducks eating the water lilies. When there are only a few ducks, then they eat only a few lilies. The water lily population, therefore, grows rapidly. When there are a few ducks and many water lilies, the ducks are well fed and their number increases. But a lot of ducks eat a lot of water lilies. When there are fewer and fewer water lilies, the ducks have less and less to eat, and their number decreases. So we have come full circle and can start again. We can record the situation at any given moment in time using a point on a plane. The first coordinate represents the number of water lilies, and the second represents the number of ducks. In fact, we get a vector field in the plane. Over time, the ducks and lilies follow a trajectory of the vector field and reach a limit cycle. The populations of ducks and water lilies eventually oscillate periodically. The belief that any motion, perhaps after a short transition period, eventually stabilizes, either by stopping or by oscillating periodically, has dominated science for a very long time. One of the first theorems in the theory of dynamical systems, by Poincaré in the late 19th century, seemed to justify this. It is about vector fields in the plane. Imagine a vector field that looks like this. In fact, we don't know the vector field everywhere, but we know how it behaves close to this circle. Take a trajectory that enters the disk. Where can it go? Well, the Poincaré-Bendixson theorem says there are two possible cases. The trajectory will either get very close to an equilibrium position, as we see here. This is what we saw for the damped pendulum. Or it must approach a limit cycle. How do we prove such a theorem? Here is the main idea. Take a point on the circle and observe the trajectory through the point entering the circle. Stop. Let's stop at a point P. Look at all of the trajectories in the vicinity of P. Is it possible that the trajectory continues and returns to the vicinity of P? Let's suppose that it indeed returns to a nearby point, Q. The arc of the trajectory between P and Q, followed by the line QP, forms a closed curve. This is the boundary of a certain area, drawn in blue. We can see that a trajectory that starts from Q enters the blue area, and then it can't get out anymore. It's trapped. In order to exit, it should cross the arc PQ. However, two trajectories cannot cross. Why not? Well, if two trajectories pass through the same point, this would contradict the Cauchy-Lipschitz theorem. There is only a single trajectory through any given point. The trajectory starting from Q cannot escape through the line QP either. There, the vector field is coming in, not going out. You can see that the trajectory from P may well return very close to P, but then it is condemned to never escape. We say, in this situation, that there is no recurrence. This is the main idea of the Poincare-Bendixson theorem. This theorem marks the beginning of what is now called the qualitative theory of dynamical systems. Even if we have only an imperfect knowledge of a vector field, we can often understand the behavior of its trajectories. In the case of the plane, everything goes well. The trajectories eventually become periodic, or they approach a point of equilibrium. But Poincare soon discovered that his theorem is valid only for vector fields in 2 dimensions. That is to say, for very small systems. For 3 dimensions and higher, we will see that the situation can be much more complicated and very beautiful. No more nice simple limit cycles. Welcome to the world of chaos. Understanding the movement of celestial objects. It is an old dream. Some people think they can read their destiny in the stars. Can we predict collisions between planets? Could gravitation eject some planets to infinity? Or should we rather expect the endless stability of the solar system? These are delicate questions. As always in mathematics, when faced with a problem that is too difficult, it is better to first look for a simpler situation. Consider this parabolic bowl. If we launch a ball, it is subject to its weight and a reaction force which keeps it on the surface. We see that the problem is analogous to that of a planet attracted to its star. This movement seems too regular to model a complex solar system with many planets. Let's take a bowl that is a bit more complicated. The ball is still subject to its weight and to the reaction force of the surface. Now the movement is really complicated. Let's take away the weight of the ball, but keep the reaction force of the surface. Listen to Pierre Duhem, the philosopher of science, presenting the work of the mathematician Hadamard, published in 1898 in an article entitled On Geodesic Surfaces with Opposite Curvatures.
A material mass slides on a surface. No gravity, no friction hinders its movement. It describes a line that geometers call a geodesic curve of the surface under consideration. When we choose the initial position of our material point and the direction of its initial velocity, the geodesic is completely defined. Imagine the forehead of a bull with protrusions from which the horns extend, and passages between these protrusions. And let's extend the horns towards infinity. We will then have one of the surfaces that we want to study.
Extend the horns towards infinity? Surely this is some fancy of a mathematician. To imagine launching a ball on the forehead of a bull with infinitely long horns. We will first use a different example, but one that is in the end quite close to Hadamard's geodesics, the game of billiards. Here is a rectangular billiard table. I shoot a ball, and then another, almost in the same way. Too simple. The two balls follow trajectories that are very close. An elliptical billiard table? Still, too simple. Here also, two balls that leave with similar initial conditions have trajectories that remain close together. It is as if we were drawing geodesics on the forehead of a bull without horns. Let's add a horn, a circular bumper. Now look at two nearby trajectories. They hit the bumper, and the first goes off in one direction and the other in a completely different direction. Their futures quickly become very different. Here is an infinite plane where balls can roll without any friction. There are three circular obstacles. Let's call them A, B, and C. Now, it's as if we were observing the geodesics on a surface with three horns. Let's take a ball and shoot it. If we aim well, the trajectory can hit A, then B, then C, then A, then B, then C, and so on. A periodic triangular trajectory. Are there other periodic orbits? Hadamard proves a beautiful theorem. He says that if you choose any word written with the three letters A, B, C, Under the condition that consecutive letters are different, for example, AB, ABC, ABC, then there is a unique periodic trajectory that visits the bumpers successively in the order dictated by the word in question. You see the complexity of the situation. For each word, there is a periodic trajectory. And there are lots of words. For example, the word A, B, C, B, C, B, C, B, C, B, C is a trajectory that pretends to hit only B and C, but once every 11 rebounds, it will hit bumper A. Of course, we must aim precisely, very, very precisely. All this makes one think of the real numbers. When we write them in decimal, some of them are periodic. These are exactly the rational numbers. As an example, 123 over 999 is 0.123123, and so on, while 2 over 7 is equal to 0.285714, 285714, 285714, and so on. Irrational numbers, when written in decimal, are not periodic. Pi, for example. Our billiard table is similar. Some trajectories are periodic and are described by a periodic word in the letters A, B, and C. Others are non-periodic and are described by an infinite word. Still others visit A, B, and C a finite number of times, and then they escape to infinity, never to return. Here is Duhem's bull.
First, there are geodesics that close on themselves. There are others that, without ever coming back to the starting point, never end up infinitely far away from it. Some keep turning around the right horn, and others around the left. Others, more complicated ones, alternate turns around one horn with turns around the other ones, following certain rules. On our bull's head, there will be geodesics that will go to infinity, one by climbing the right horn, others by climbing the left horn.
Imagine the moon, that has always been the Earth's companion, suddenly deciding to shoot off towards infinity.
Despite this complication, if one knows with an absolute accuracy the initial position of a point on the forehead of this bull and the direction of the initial velocity, then the geodesic that this point will follow during its movement will be unambiguously fixed. It will be quite different if the initial conditions are not known mathematically, but practically.
Appreciate the subtlety, not mathematically, but practically. Watch these geodesics that begin at the same point and start almost in the same directions. They follow almost the same path for a while, and then they separate. The green, red, and blue geodesics have completely different futures.
If a point is launched on the surface in question from a position that is given geometrically, with a speed that is given geometrically, then mathematical deduction can determine the trajectory of this point and determine if this trajectory moves away to infinity or not. But for the physicist, this deduction is forever unusable.
So far, all of this applies to geodesics or billiard ball trajectories. Can this be applied to everyday life or, for instance, to the movement of the planets? The question of telling my future is still unanswered. In the early 1960s, the young American mathematician Stephen Smale was working on the beach of Copacabana when he made a discovery. He discovered a horseshoe. Not in the sand, of course. In fact, this horseshoe is an abstract mathematical object. It is another simple idea that attempts to reduce chaos to its most elementary expression. We must first explain an old idea dating back to Poincaré. Here is a vector field in space. A trajectory that starts on the green disk must travel all the way around before returning to the disk, and then taking another trip, and so on. For each point x of the disk, we can observe the trajectory that starts from that point, and wait until it hits the disk again at a new point, p of x. A few seconds later, this new point is again transformed by t, and we get a third point, t of x, and so on. After each trip, the point is transformed by t. Instead of studying the trajectory in space, we study the sequence of returns to the disk. This is much easier to draw. We replace the dynamics of the vector field in continuous time by the dynamics of the transformation t in discrete time, 0, 1, 2, 3, and so on. This is often much easier to understand. Here, the transformation t is a rotation by 1/3 about the center of the disk. The central trajectory corresponds to the fixed point of the rotation, the center of the disk. Other trajectories are also periodic, but it takes them 3 times longer to return to their starting point. This is because we are rotating by 1/3. Here, the transformation t is a similarity. The trajectories are no longer all periodic. On the contrary, they approach the central trajectory while spiraling around it. We say that the central trajectory is stable. Here is an example of an unstable trajectory. The transformation t squeezes the kitten along its width and stretches the kitten along its height. The center of the disk is a fixed point, so its trajectory is periodic. You see that the trajectories located on the horizontal axis approach the fixed point, while those on the vertical axis move away from it. Poor kitty. Now let's look at the horseshoe. Watch how this square is deformed over time. The transformation T combines a scaling, a contraction, and also a fold. When the square arrives back on the original disk, it has taken the form of a horseshoe. Now watch the behavior of the square as we go back in time by the inverse transformation. A scaling, a contraction, a folding, but this time all in the other direction. Let's try to envision the future and the past of the square. After one trip, as we have seen, it becomes a horseshoe. After one trip the other way, into the past, it also becomes a horseshoe, but turned by 1/4. The two small vertical strips you see at the intersection of the square and the horseshoe are also compressed, scaled, and folded. The behavior into the past is the same. And this whole structure is repeated an infinite number of times. A very complicated horseshoe. How can we understand its dynamics? Let's call this strip A and this strip B. Well, the amazing thing is that we almost get the same results as Hadamard's geodesics and billiards. For each finite sequence of A's and B's, even when allowing repetitions, for example, BA, BB, there is a periodic point that will follow this route exactly. In this example, we have a point of B that jumps to A, then jumps to B, then jumps to B again, and then jumps back to the starting point. Here is the only point of A that always remains in A. It is a fixed point. This fixed point is in B. Here is a trajectory that alternates between A and B. But, as with billiards, this is not limited to finite sequences. Give me an infinite sequence of your choice, BB, AA, BBB, AA, BA, BA, and so on, well, there is a point following exactly this route in its future. When you think about it, this is incredible. Every possible future is true for at least one person. Oops, I meant for at least one point. Prediction is impossible because everything is possible. Free will rediscovered. Anything is possible? That's a fine slogan for chaos. Thank you, Mr. Smale. Smale realizes that it is not always necessary to know things exactly in order to understand them. A distorted picture is often enough to recognize a face. He shows that the horseshoe is stable. Mind you, this does not mean that the trajectories are stable. On the contrary, trajectories are very, very sensitive to their initial conditions. What we mean here is structural stability. Distort Mr. Smale's picture and you will still recognize him. On the right, we have the original horseshoe. On the left, another horseshoe, slightly modified, is being formed. After all, when you stretch the square into a rectangle and then fold it in the form of a horseshoe, you can do it in any one of many different ways. This is somewhat analogous to the situation where we study two solar systems where the planets have slightly different masses. Two almost identical horseshoes. We can do exactly the same as we did with the original horseshoe and draw strips, A' and B'. And it can be shown in the same way that the trajectories on this new horseshoe are still described by sequences of A' and B'. The modified horseshoe is just as chaotic as the original one. Chaos is really there, indestructible. In fact, Smale shows that the movements on the two horseshoes are somehow identical. Look, the two trajectories, right and left, follow the same choreography. They visit the same A', and the same B'. We can match any trajectory of the second horseshoe to some trajectory on the first horseshoe and vice versa. It is in this sense that the structure is stable. We can deform the horseshoe any way we want, and not only does it remain chaotic, but it keeps the same dynamics as before. Individual trajectories are unstable, but the dynamics as a whole is stable. Early in the 20th century, Poincaré, with characteristic flair, explained how it is possible to understand a dynamical system even if one does not know it very well.
You ask me to predict the phenomena that will occur. If I had the misfortune to know the laws of this phenomena, I could only get there by intractable calculations, and I would not be able to give you an answer. But as I am so lucky as to be ignorant of them, I'll answer right away. And what is most extraordinary is that my answer will be correct.
Coexistence of chaos, and hence the instability of individual trajectories, with structural stability, a global property, is absolutely remarkable. I'm unstable, but the world around me is stable. Very reassuring. When we look at the movement of the atmosphere, we quickly realize that it is infinitely more complex than that of the solar system. The atmosphere is a fluid that has, at each altitude above each point of the Earth's surface, a speed, a density, a pressure, a temperature, and so on. All of this data varies over time. It is, of course, impossible to understand this practically infinite amount of data. It is almost as if we were in a space with an infinite number of dimensions. to understand something about it, we must make approximations. In 1963, Edward Lorenz simplified and simplified and simplified the problem again. He simplified it to such a degree that there is no guarantee that his equation has anything to do with reality. His model of the atmosphere was reduced to just three numbers x, y, and z. The evolution of the atmosphere was reduced to a simple equation. Each point, x, y, z, in space, represents a state of the atmosphere. The evolution follows a vector field. For example, and this is only an example, the first coordinate could represent the temperature, the second, the wind speed, and the third, the humidity. Over here, it is cold, breezy, and rainy. Here, the opposite holds. When we follow a trajectory of the field, we are following the evolution of the weather. The weatherman just needs to solve a differential equation. This is what Lorenz saw when he studied his model. Does this have anything to do with real weather? That is far from clear. This is what physicists often call a toy model, used to try and understand the broad outlines of some complex behavior. In fact, Lorenz only had these sorts of graphs to look at because his computer in 1963 was quite primitive. Let's look at two atmospheres, represented by the centers of these two balls that are extremely close together, so close they are almost identical. Let's observe what happens to them. At first, the two evolutions are almost indistinguishable. But then, they split up significantly. The two atmospheres become completely different. This then is chaos, sensitive dependence on initial conditions. In 1972, Lorenz was going to present his work at a prestigious conference, but he was late in sending in the title of his lecture. The organizer, Philip Merlis, was in a hurry to send the program to the participants, so he chose a title for Lorenz. Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The butterfly effect was born. Mathematical concepts are often not well understood by the general public. The image of a small, frail butterfly having an influence on the world is very poetic. The idea was very successful and has been endlessly modified. There is always a butterfly, but sometimes it comes from Africa and sometimes from China, and it is responsible for disasters in New York or in Chicago. Interesting. The idea found its way into literature, music, and movies. The list of films based upon this idea is endless. It generates a lot of emotion in Babel, the 2006 film by Alejandro González Inarritu. The insignificant incident of a gunshot in Morocco will change the lives of an American couple, a Mexican nursemaid, and a Japanese girl. An interplay of small causes and large consequences. How chance determines the fate of humans. Unfortunately, Only one half of Lorenz's message made its way to the general public. Can chaos theory be limited to the statement that it is impossible to predict the future in practice? How could scientists resign themselves to such an admission of failure? Lorenz's message is much richer. Here are two trajectories of the Lorenz system, one blue and one yellow, that do not start from very similar initial conditions. Let's erase, say, the first 10 seconds of the movement, and then let's observe what happens. What do we see? The trajectories are indeed very different. They seem a little crazy and very unpredictable. But they accumulate on the same butterfly-shaped object. This accumulation does not seem to depend on the initial position. The trajectories seem to be attracted to this butterfly. This is what is referred to as the Lorenz attractor. A strange attractor. Here is a positive scientific phenomenon, one not as famous as the butterfly effect. Instead of observing just two trajectories, let's look at many more. Look at all these balls, each one of them representing a simplified atmosphere. After a while, they all accumulate on the same butterfly. A very nice object that we can admire endlessly. These are real problems for mathematicians and for scientists also. Instead of describing the future starting from a given initial position, which we know is impossible, we will instead try to describe the attractor. What does it look like? How do the internal dynamics work? In the 1970s, Berman, Guckenheimer, and Williams proposed a simple model for trying to understand the Lorenz attractor. Here is a strip of paper. Let's fold it, and cut it, and glue it together. And we have a special object in space. Let's go to the starting line. Here we go. We drive, and a little while later, we are back at the starting line. But we are at a different point of the starting line. From here, a new path starts. Our position on the starting line is given by a number x between 0 and 1. At 0, we are on the left, at 1/2 we are in the middle, and at 1 we are on the right. If we start from the point x, then we will return to the point 2x if x is smaller than 1/2, and we will return to the point 2x minus 1 if x is larger than 1/2. In other words, when the car moves, the points where it meets the starting line are doubled at every turn, except we need to subtract 1 if the result is greater than 1. It's a bit like the horseshoe. The dynamics in continuous time get replaced by dynamics in discrete time. Namely, by the successive places where we cross the starting line. Look, we start off from 1/3. we arrive at 2/3. And then we arrive at 4/3, but we must subtract 1, that is to say, we arrive at 1/3. So, we are back to our original starting point after 2 rounds. Thus, we have a periodic trajectory of period 2. Here is a trajectory of period 18. Periodic trajectory passes successively through the left and right ears following a certain sequence. Well, it can be shown that all sequences are possible. And of course, not all trajectories are periodic. Whatever the infinite sequence of lefts and rights, there is a trajectory that follows that destiny. What is the relationship between the Lorentz attractor and the model made of strips of paper? Well, it wasn't until 2001 that the mathematician Tucker showed that the paper model accurately describes the movement on the Lorentz attractor. For each trajectory in the Lorentz attractor, there is a trajectory in the paper model that behaves in exactly the same way. Is it possible that the movement of the atmosphere can be reduced to continually doubling a number x between 0 and 1 and subtracting 1 if the result is greater than 1? Of course not. All of this is much too simplistic, but it is an illustration of the phenomenon. Simple things? Mathematicians love them. Why has the butterfly effect become so popular? Perhaps because it gives us back our freedom. The legacy of Newton's cold determinism sometimes leads to a kind of fatalism. The Lorentz butterfly claims that, small as we are, we can have an influence on the world. Good news for us. Listen to Ed Lorenz telling us about his concept of chaos in 3 steps. If a single flap of a butterfly's wings can be instrumental in causing a tornado, so also can all of the previous and subsequent flaps of its wings, as can the flaps of the wings of millions of other butterflies, not to mention the activities of innumerable much more powerful creatures, including our own species. We have already seen that the public understands this first point very well. If a flap of a butterfly's wings can be instrumental in causing a tornado, it can equally well be instrumental in preventing it. Yes, but the third point is the most important, and this one provides work for scientists. More generally, I am proposing that, over the years, minuscule disturbances neither increase nor decrease the frequency of occurrences of various weather events, such as tornadoes. The most they may do is to modify the sequence in which these events occur. Let's return to Lorentz's model. Remember, each point in space represents a state of the atmosphere. In some areas, the weather is fine, and in others, a hurricane blows. Suppose that the area corresponding to a hurricane is in this little ball. Let's take an initial climate condition and let's observe the trajectory that results. Occasionally, a hurricane occurs. That is, when the trajectory enters the ball. Let's measure the proportion of the time between 0 and t when a hurricane rages. It seems difficult to guess at which specific moments the trajectory enters the ball. but the average time spent inside the ball converges to a limit as the interval of time measured becomes larger and larger. Here, the average is 5.1%. Now we take a different initial condition and do the same calculation. Well, again the trajectory spends a certain amount of its time inside the ball and the average tends to a limit. Oh, how about that? The average is the same as before, 5.1%. Let's try it with yet another trajectory. It works. We obtained the same limit, and yet the trajectories are very different. They are sensitive to initial conditions, to the flaps of the wings of the butterfly. We add another ball, pink, maybe, and a third one, green, perhaps corresponding to heat waves or to snow. As a trajectory unfolds, it crosses the balls in a certain order. To see what happens, let's watch 3 trajectories, each starting from a different initial condition. Look. On every trajectory, the situations hurricane, snow, heat wave alternate incomprehensibly and in a different way for each trajectory, impossible to understand. But the proportions of yellow, green, and pink converge rapidly into the same limits. Here are the averages: 5.1, 14.03, and 7.4%. It is as if we were randomly picking balls, yellow, pink, or green, from a bag filled to those proportions. Listen to Lorenz again. Minuscule disturbances neither increase nor decrease the frequency of events such as tornadoes. The most they may do is to modify the sequence in which these events occur. This is a scientific statement. The purpose of the forecast has changed. We now try to predict averages, statistics, and probabilities. The idea is that these statistics are, perhaps, insensitive to initial conditions. They are unaffected by the flapping of the wings of Brazilian butterflies. This hypothesis, as yet unproven, of the possible coexistence of a meteorological chaos, where the future movements are sensitive to initial conditions, with a statistical stability insensitive to initial conditions, took a long time to be formulated mathematically. Lorenz was probably a little embarrassed by the simplistic, to say the least, theoretical side of his 3-parameter atmosphere. With the help of 2 physicists, Howard and Marcus, he developed a real physical system. That is, it is real, even if it is still simplistic and far removed from true weather phenomena. Here is a mill. It consists of a wheel with buckets suspended evenly around it. Each bucket has a hole in the bottom, and the water will run out of the bucket. It runs more quickly when the water level is higher. We open a valve at the top and watch how the mill moves. It sometimes turns to the right and sometimes to the left. We seem to be totally incapable of predicting which way it will be turning in just a few seconds. The movement seems totally erratic, unpredictable, chaotic. In fact, there is a relationship between the mill and the Lorentz attractor. Let's choose three numbers to describe the mill. For instance, the angular velocity and the two coordinates of its center of gravity. The evolution of these numbers traces out a yellow curve in 3 space. Is it not incredible? Our mill moves like a butterfly. Let's change the initial position imperceptibly. Again, all the buckets are initially empty. The left wheel is 2 degrees off of vertical, while the right wheel is only 1.9996 degrees off of vertical. We would need a good microscope to see the difference. Yes, there is clearly a sensitive dependence on initial conditions. After a while, the two mills have completely different behaviors. Let's see if Lorentz's statistical statement is true for the mill. Our two mills take off from almost the same position. Let's measure their speed. For example, 25 times per second for 5,000 seconds, so 125,000 observations in total. For each observation, we note the rotational speed of the wheel. One simple idea is to do what statisticians do. We use a bar chart to illustrate the distribution. We divide the possible speeds into 35 equal intervals. We count the number of times that the measured speed falls in each interval. Here is the result. Some intervals appear to be visited more than others. Our two mills behave in very different ways. They have a sensitive dependence on initial conditions. But we see that the two sets of data, although different, are statistically identical. The bar charts tend to become identical. It works. Lorentz seems to be right. When the statistics of a trajectory are insensitive to initial conditions, we say that the dynamics have a Sinai-Ruel-Bowen, or SRB, measure. The goal of a forecaster is then to determine these statistics. For example, let's observe the evolution of the temperature over time, the temperature being one of the coordinates in Lorentz's equation. We draw another bar chart, as we did with the mill. For each temperature range, we note the proportion of observations that fall within this range. Even if we consider trajectories that are quite different from one another, after a while, the charts tend to become identical. The Lorentz attractor has an SRB measure. It is as if the temperature was changing at random, but with very specific probabilities. But there is a lot left to do mathematically and physically. We must find these probabilities and these distributions in order to be able to say something useful. Let us hope that we have done justice to Lorenz, who did not merely say that the future depends heavily on the present. Many people before him said that. He also, and more importantly, contributed the following idea. By refocusing on statistical issues, science can still make predictions. There are many kinds of dynamical systems. Some are complicated, others are not. Watch this vector field in space. The field depends on a parameter a. Let's start by choosing a equal to 0.3 and watch what happens for a large number of initial conditions. After a while, they are all attracted to a single periodic trajectory. No chaos here. There certainly is an SRB measure, as all initial conditions wind up moving along a closed curve. Let's slowly change the parameter a. We see that, for a equal to 0.335, the periodic trajectory splits apart. not for all dynamical systems, but for most dynamical systems. Again, we must temper our enthusiasm. Watch this vector field. Here is a trajectory. All is well. It accumulates on a butterfly, as we have seen before. As the initial condition moves slowly along the blue axis, everything behaves as it should. The trajectory always accumulates on the orange attractor, even if it takes a little while to get there. We can easily check that the statistics have not changed. But, all of a sudden, without warning, a surprise. The trajectory accumulates elsewhere, on another attractor that has nothing to do with the first. Space appears to be split into two regions. If one starts with a point in the first region, the trajectory accumulates on the orange attractor. If we start in the second region, we end up at the green attractor. In other words, there is no SRB measure since the long-term behavior depends on the initial condition. In fact, there are two SRB measures. For certain initial conditions, statistics follow the first measure. For other initial conditions, the second. In the 1990s, the Brazilian mathematician Jacob Pallas formulated a whole set of problems that, if resolved, would allow for a global vision of chaos. One of these says that the situation we have just encountered should be typical. In all dimensions, a typical vector field should have only a finite number of attractors. A typical initial condition should be drawn to one of these attractors. Each attractor should have a Sinai-Ruel-Bowen measure that describes the asymptotic statistics of the typical trajectories that fall into that attractor. A whole group of mathematicians is hard at work on these conjectures, and they are being solved methodically, bit by bit. A global picture seems to be emerging. Is this picture too optimistic? Time will tell. Today, we no longer think of determinism as the evolution of an individual trajectory, but rather as the evolution of a whole collection. Sensitivity of trajectories to initial conditions is compensated for by a kind of statistic stability of the collection of trajectories. Did Buffon in 1783 not foresee this when he wrote this magnificent sentence about a complex and chaotic world that one has to try and understand globally?
Everything happens because with time everything meets, and in the free range of spaces and in the continuous succession of movement, all matter is stirred. Any form given, all figures printed. So everything is coming or going, all is joined or running away, all is combined or opposed. Everything happens or is destroyed by relative or contrary forces that are the only constants. And balancing without harm, they animate the universe and make it into a theater with ever new scenes and objects incessantly reborn.